Swayam Prabha. Digital India. Educated India.
In the previous lecture, we have discussed the method of solving dynamic force analysis problems of plane mechanisms. We have seen that dynamic force analysis problems mean that when the complete motion of a system is known, to find out the unknown joint forces in the mechanism and also the externally applied force or moment which causes the system to move in the manner prescribed. In this, of course, we have to keep in mind that for a mechanism or a machine with single degree of freedom, only one component of externally applied forces can be independently found out. On the other hand, if we have more degrees of freedom, the number of unknown forces externally applied can be more. Now, in the previous lecture, we adopted a technique of using graphical procedures. Though we get answers which are often adequately accurate and precise for design purpose, it becomes very difficult if we have to repeat the analysis again and again for a large number of situations. For example, if a mechanism is moving, continuously rotating, say a crank rocker mechanism, then if we have to find out the forces for the complete cycle of the system, then we have to repeat the force analysis problem for each and every position of the crank. Maybe if you have to take the cranks at every 2 degrees, then we have to solve the problem for 180 times. Apart from that, whatever may be the procedure or the equipment we use, a graphical analysis will always have some limitation from the point of view of accuracy of the results. Third, if we have to optimize a system or we have to achieve an optimal design, then again doing the problem or solving the problem by graphical approach becomes difficult. So in today's lecture, what we will do, we will solve the same problem of dynamic force analysis adopting an analytical approach. So today's lecture will be dynamic force analysis by analytical method. In principle, it is the same. We write down the equations of motion of each and every moving link. Since in plane motion, every rigid body will have 2 linear components of accelerations of its center of mass and 1 component of angular acceleration, we will have 3 equations of motion for each such rigid body. So, if there are n number of links, j number of joints, then you know that for constrained mechanism, the following relationship has to be satisfied. We will take up such simple cases only. in this lecture, and our objective will be to find out the unknown joint forces and one unknown externally applied force or moment if the system taken is constrained, that is there is only one degree of freedom. Then number of moving links will be n minus 1, and so the number of equations we will get will be equal to 3 into n minus 1. Since each joint will have two components of forces, we will have number of joint forces is equal to 2 into j, and externally applied that is unknown or to be found out will be 1. So, to find out 2j number of unknown joint force components and one unknown externally applied force as moment, total number of unknowns will be equal to 2j plus 1. And from this relationship, which has to be satisfied for a system with single degree of freedom, we know that 2j plus 1 is equal to 3 into n minus 1, that is the number of equations of motion. So, it is very clear that we will have as many equations as there are unknown quantities to be found out, and so the equations can be solved and results can be found out. Now, let us explain the procedure with the help of an example of 4-link mechanism. Let our mechanism be this. With this is the moving link 2, this is the moving link 3, and this is the moving link 4, and the fixed link we always call 1, as you know. At this particular instant, the angles made are theta 2, theta 3, and theta 4. The length of the links are known. The location of their respective center of masses are, say, G2, G3, and G4. We also give the dimensions of this part from O2 to G2 as, say, D2, G2 to A as F2, A to G3 as D3, and this part F3, this is D4, this is F4. So, now let the externally applied forces components are M2, say let this be the only externally applied force in this case. Even if there are other forces acting, then they have to be prescribed. So, to keep the problem simple for explaining the procedure, let us assume that only one external force is acting. In this case, it happens to be a moment. We also know, or we have done in the previous course on kinematics, that if the angular acceleration of one of the members, say in this case let it be link 2, is given as alpha 2, its velocity also is prescribed as omega 2, then it is possible for us to find out the acceleration of the various mass centers, and let these be let the acceleration components of the mass centers be ag2x and ag2y. Of course, we have assumed x in this direction, y in this direction. The acceleration of this center of mass as ag3x and ag3y. Acceleration of this point components are ag4x, ag4y. Angular acceleration of this is already given, prescribed, and we can find out the angular acceleration of other links. So, this figure now contains all the kinematic parameters like acceleration components, the configuration, and also the externally applied moment. Now, we should draw the free body diagram of each and every moving link before we can write down the equations of motion of each of these. So, we next draw an exploded view of this link or mechanism. And the joint forces, say this particular joint which connects this link 2 with link 1, the components of forces be P12x and P12y. It means it is the joint force from link 1 on link 2 in the x direction and y direction. Similarly, we write here P32, that means force from link 3 on link 2, its component along x, and P32y. Now, we know that force according to Newton's third law between two bodies will be always equal and opposite. So, whatever force is coming on this link from link 3 at this point, exactly opposite and equal force will act on the other link. So, the force in the x direction at this point will be P32x, but in this opposite direction this will be P32y. Now, similarly, force on link 3 from link 4, it will be P43x, this is P43y. You can see always that the first subscript is the body which is applying the force, and second subscript is the body on which the force is acting. So, now on this point again it will be just equal and opposite of the forces acting here. And here again it will be P14 x and P14 y. Over and above this, there is one moment acting on link 2, which also we have to find out. So these are the unknown force components we have to determine. That means how many are unknown there? 2 here, 2 here, so 4, 2 here, 6, and 2 here, 8, and 1 M2. So now the equation of motion of each member can be written by Newton's second law. So for the second link, in the x direction, total force acting is P12x plus P32x, and this must be equal to mass of the second link into Ag2x. We should remember that there can be externally applied forces apart from only M2, but we have to prescribe them. We cannot find more than one external force component. So in place of, instead of M2, we could apply a force in this direction or a force in this direction or more than one force acting, but then only one can be kept as an unknown quantity. Here, for the sake of simplicity, we have not applied any other force except the only one which we have to find out. In the y direction, the equation of motion will be P12y plus P32y, and that must be equal to the total force in the y direction given by the mass of the body into the acceleration of the center of mass in the y direction. And if you consider the angular motion, then about the center of mass, which is here, total moment will be how much? P12x multiplied by this, that is the arm, moment arm. Since this is d2 and this angle is theta 2, so this moment arm is d2 theta 2. So the moment about the center of mass of this component of this force will be P12x d2 sine theta 2. This component will produce a moment in the opposite direction, so you have to put a minus sign, P12y, and the arm, moment arm will be d2 cosine theta 2. This force component will produce again a clockwise moment, so it will be P32x, and this length is F2, F2 sine theta 2 is this, and this is also in the clockwise direction, so it should be minus, but this one is again in the anticlockwise direction, that means the direction in which it is accelerating with angular acceleration alpha 2. And this is the total moment when you add the externally applied moment M2, and this whole thing is nothing but the moment of inertia of the object about its centroidal axis, which is M2 into K2 square, where K2 is the radius of gyration of second link into alpha 2. So thus you can see that we have three equations for the second link. Exactly in the same way, when we go to the other links, we can write down similar equations like minus P32 x plus P43 x is equal to M3 A G3 x minus P32 y plus P43 y is equal to M3 A G3 y. And again taking moment, it will be P43 x, this is F3, this length is D3, and this angle is theta 3. So therefore, the moment term is this, it will be equal to F3 sine theta 3 is the moment of this, about this. P43 y will also apply a moment about this with this as the momentum. This also will produce clockwise moment P32 x d2, momentum will be this, and this is equal to d2 sine theta 3. This will also produce a clockwise moment, anti-clockwise moment, that is P32 y d3 cos theta 3. There is no other external moment acting here, so the total moment in the anti-clockwise direction is this, and this must be equal to moment of inertia of the link about its centroidal axis, that is m3 k3 square, where k3 is the radius of gyration and alpha 3 is the angular acceleration. Now I have already mentioned that since the kinematics is completely solved, we know all the acceleration components and the angular accelerations. For the last link, exactly in the same procedure, we will get total equation in the x direction as P minus P43 x plus P14 x, it must be equal to M4 A G4 x. In the y direction, we will have minus P43 y plus P14 y and is equal to M4 A G4 y. And similarly, the moment equation will be moment equation, that means the total moment about the center of mass will be minus P43 x, sorry, it will be plus because it will be anti-clockwise. So P43 x into d4, and moment arm is this much. This is d4 and this angle is theta 4. So d4 sine theta 4. This one will produce a clockwise moment, so it will be minus P43 y d4 cosine theta 4. This will produce again an anti-clockwise moment, that means a moment in the direction of alpha 3 or alpha 4. And momentum will be F4 sine theta 4, and y component here will produce a clockwise moment, that means opposite to the algebraically positive direction of alpha 4. So it will be and this represents the total moment acting on link 4 and which has to be equal to moment of inertia, which is m4k4 square into alpha 4. So, we have 1, 2, 3, 4, 5, 6, 7, 8, 9 equations, 9 linear equations in 9 unknown quantities p1 to x, p3 to x, p1 to y, p3 to y, then p43x, p43y, p43 32x, 32y and 14x and 14y. So, we have already drawn all those forces which are unknown, and m2 is the other unknown quantity. Since you have a set of 9 equations in 9 unknowns, they can be all solved, and the unknown force m2 and all the unknown joint forces can be uniquely determined. The advantage of this methodology is that once the set of equations are written, and of course, we have not shown it here because it is a part of kinematic analysis, you have to also get the expression for alpha 3, then acceleration of the mass centers in terms of theta 2, theta 3, theta 4, theta 2 dot, theta 3 dot, theta 4 dot, and the input acceleration theta 2 2 dot, which is alpha 2. So, once that is done, the computer can solve the equations and give you the values. Only thing what you have to do, you have to keep on changing one of the parameters like theta 2 say for example, so that for every configuration the answer can be found out with the help of computer, and this can give the whole system's complete cycle of motion, and you can find out the unknown forces. That is the advantage of the analytical technique. The answers will be quite accurate depending on the accuracy of the input values, depending on the accuracy of the physical parameters we have given. There is no other limitation, and you can also sometimes even solve problems keeping in mind optimization of the machines, its optimal design, minimization of forces, maximization of some other quantities, whatever it may be. In the graphical procedure, it becomes extremely difficult to repeat it hundreds of times for getting one complete cycle's analysis. Once the forces are known, then of course a designer can then design the bearings and other joints suitably so that such forces can be sustained. It is also possible, which we are not going to do here of course, that once you have the forces on each link, it is possible to also find out the stresses which they are subjected to, and their design can be taken care of. So, this brings us to the end of module 1, in which our objective had been dynamic force analysis, that is a system which motion is given, system parameters are known, we were able to find out the unknown forces in the joints and one unknown force quantity which causes this motion which is prescribed. As I mentioned that if the number of degrees of freedom are more, then we can have more number of externally applied forces which are unknown and can be solved for. In the next lecture, we will start a new module where we will start studying the motion of rigid bodies in 3 dimension, because you have seen here that the whole system of motion was contained in one plane or parallel planes, and the situation was very simple. But we will see that rigid bodies have many new characteristics and many new properties when we consider the motion to be in 3 dimension.